Good morning, good afternoon, whatever it is for you. As you know, we have 10 minutes to give a talk. I don't think this is enough time. So that I have thought that the best thing to do would be to provide you with a summary on according to myself, of course, because I am biased, a nice idea that we recently had. The effect that we have been working on is related to the emission of gravitational waves. And you know that these waves are very fashionable since a couple of years. I worked on them for much longer before than that. And with a very bright PhD student of mine who is working in China, Alejandro Torres, and other people, we have managed to put together the first results on the possibility of measuring what we have coined in quotation marks, because this is an idea which was already, I'm not going to say in the market because I don't like that expression, but was out there. And I'm going to show you the first picture that I have here. The paper has been submitted to the archive, as you can see, but the order of the authors has been shifted a little bit because Alejandro is now the first author. First of all, because although I initially motivated the idea and put it forward, etc., the truth is that Alejandro has done a lot of work, and it would not be fair to be first author, so that Alejandro Bloom has jumped here to the first place, and we have moved a little bit around the authors. But it's been a teamwork, and everybody has contributed a lot, and it would be unfair to say whatever. Anyway, everybody is nice, everybody has contributed a lot, and I think it's a nice idea. So the basic point is that when people think of measuring gravitational waves, for some reason we just assume that these sources, that typically is going to be a binary, we just regard these sources to be fixed, emitting these gravitational waves, and these gravitational waves are propagating towards us. Okay, this is probably a wrong picture. Why? Because most of the sources, most of the galaxies, galactic nuclei, globular clusters, you name it, are going to be moving relative to us. And they're going to be moving at a relatively large speeds. And this is where I want to show you, if I manage to do that, the second plot of the paper. Let me see if I manage. Okay, there you go. So on this axis, which is the y-axis, or what could be the p-axis or the r-axis according to your mood, we show you the velocity dispersion in kilometers per second, and here we have the z, so the redshift, and assuming a given cosmology, we have the conversion in millions of parsecs here. These are real data out to a redshift of about 1, which is not bad if you consider the translation into parsecs. This is 2,000, 3,000, 4,000, 5,000 parsecs around it. And we can see, so these are classes of galaxies, okay? So each point or square, whatever you want to call them, here represents a cluster of galaxies. So we have many of them contain up to thousands of galaxies. And you can see that assuming a velocity dispersion, this is something that you can actually observe or theoretically derive by assuming the real equilibrium. We can see that most of these galaxies are moving at a relatively large speed relative to us. Okay, so this is important because gravitational waves from a source moving at a relatively high velocity can suffer special relativistic effects such as aberration. Okay. Now, in recent papers, we investigated several relativistic effects related to a moving source of gravitational waves. Now, I will probably in somewhere, I don't know, I can provide you with the links. But the most important thing about this is that we have managed to do one exercise in this paper. We have managed to address the impact on the modes of source, which we have chosen to be a circular, and I would like to underline that, a circular string mass ratio spiral. As you know very well, string mass ratio spirals are very, very likely not circular. So this is important because of what I'm going to show you. Let me find the picture if I manage to do that. In any case, so in this work, we have shown that the signal from a moving source will have its higher modes excited, in particular the 3-3 mode and beyond. We derive expressions based on a previous paper by Alejandro, in which well, he gave a very nice theoretical description of the context in which this is embedded. And we have measured the possibility of detecting one of these things. So in this figure 2, I am struggling to find it, but it must be the age or whatever. And for some reason this is not moving now. Okay, now it is moving. Yes, this is figure 2 now. And in this figure, I am showing you, well actually Alejandro is showing you, or we are showing you, the mismatch. So, you know, mismatch is 1 minus m, between the putative, so the, if you want, a theoretical perfect waveform of an extreme mass region spiral, which would be at rest, and the observed waveform of an extreme mass region spiral moving with a typical velocity of about 1,000 kilometers per second. We're showing you the mismatch and the signal to noise ratio, okay? And we address here, we show the these two quantities for different viewing angles of a given source, theta. Okay, now we have only 2 minutes left, so let me jump to the last figure. In this figure, what we do is to depict the confidence ellipses at a 1 sigma level for the measurement of the masses of the black holes. Here we have m2 and m1, and this is the velocity in kilometers per second. And by the way, this is times 10 to the minus 7 over here and over there. Again, we have a source at rest, which is the solid blue line, and a moving source, which is the dotted red line. For the moving source, the masses measured represent, in this case, the Doppler shifted masses as seen in the observer frame. So, what can we derive from these results? What we can derive is that since the effect might be significant for extreme mass region spirals, the inclusion in the waveform can be used to measure the peculiar motion of the host galaxies. What does this mean? This means that we have galaxies or classes of galaxies very, very far away from us, because we're talking about, you know, that with extreme mass region spirals, in principle, we can go to a redshift of 1, being not pessimistic, and being extremely optimistic to a redshift of 4, okay? So that if we can detect the deviation in the waveforms from a source at rest as compared to a source which is moving relative to us, we can extract information about that relative motion, which means that we can have a very detailed mapping of the velocity dispersions of classes of galaxies which are not accessible to our old friend, the photon. Now, I would like to, I had something else to show, but I will not find it now, of course. But the interesting thing is that, in these figures, yes, I forgot that we're assuming a circular stream mass spiral with a signal to noise ratio of about 20, okay? Now, for eccentric stream mass spirals, the distances should be significantly larger. Why? Because the eccentricity is going to enhance this effect, okay? And the 10 minutes is over now, and I guess I can't say anything else. I'm going to try to leave a link to the papers somewhere. Thank you. Bye-bye.